Assalamualaikum sir. Today it is my pleasure to present our group project on determine the number of reflexive relations on a finite set. First, I would like to introduce our group members. Our group consists of MD Sadman Sadat and Habibul Bashar Didar. I am Nusra Jahan and I am the first speaker of our group. We are sincerely grateful to our respected teacher, Dr. Nafis Sadek, for giving us the opportunity to work on this interesting topic. Now I would like to begin with the objectives of our project. The objectives of our project are simple and clear. First, we want to understand the basic concept of relations in district mathematics. A relation is an important idea because it shows how elements of a set are connected to each other. Second, we want to define reflexive relation clearly. A reflexive relation is a special type of relation where every element is related to itself. Third, we want to analyze Cartesian products because every relation on a set comes from the Cartesian product of that set with itself. Another objective is to determine the number of reflexive relations on a finite set. This is actually the main focus of the project. So these are the main objectives of our project. Now I would like to move to the introduction part and concept in district mathematics. If A is a set, then a relation R is any subset of A cross A. Here A cross A means the Cartesian product of the set with itself. It contains all possible ordered pairs formed by the elements of the set. Now a relation is called a reflexive if every element of the set is related to itself. In other words, for every element A in A, the ordered pair AA must belong to the relation R. For example, if A equal 1, 2, 3, then a reflexive relation must contain the pairs 1, 1, 2, 2 and 3, 3. These pairs are necessary. Without them, the relation cannot be called a reflexive. So the main idea is very simple. In a reflexive relation, each element must have a relation with itself. Now I would like to explain the theoretical background of this topic. Let A be a finite set with n elements. Then the Cartesian product A cross A contains n squared ordered pairs because each element of the set can be paired with every element including itself. Now for a relation to be reflexive, the pairs A1, A1, A2, A2, AN must always be included. So among the total n squared pairs, there are n required pairs. After including these required pairs, the remaining number of pairs is n squared minus n. Now each of these remaining parts has two choices. It may be included in the relation or it may be excluded. Since each of the n square and pairs has two possible choices, the total number of reflexive relations becomes 2 square into n square minus n. So this is the formula of determining the number of reflexive relations on a finite. To conclude my part, I would like to say that a reflexive relation is a relation where every element is related to itself. If a set has n elements, then A cross A has n squared ordered pairs. Among them, n's are important for reflexivity, and the remaining n squared n pairs are optional. That is why the total number of reflexive relations on a finite set is 2 to the power n square minus n. This formula helps us understand the structure of reflexive relations in a simple mathematical way. So through this project, we were able to understand the concept of relation, reflexive relation, Cartesian product, and the formula for counting reflexive relation.
Hello everyone, it's Sadat. Today I'm going to present our topic on reflexive relation and how we can calculate the number of reflexive relation on a set using a simple mathematical formula. One of our group member already explained the introductory part, so I'm going to the example. Here we take A is equal to 1 and 2, so A cross A gives all possible ordered pairs 1 1, 1 2, 2 1 and 2 2. For a relation to be reflexive, each element must be related to itself. So 1 1 and 2 2 are the required pairs. The remaining pairs 1 2 and 2 1 are optional. Since there are two optional pairs, the total number of reflexive relation is 2 square, which equals 4. On this slide, we can see all the reflexive relations for the case when n is equal to 2. This set is A is equal to 1 and 2. So for a relation to be reflexive, the pairs 1 1 and 2 2 must always be included. These two are the required pairs because each element must be related to itself. Then we have two optional pairs 1 1 and 2 1. By adding none, one, or both of these optional pairs, we get the four possible reflexive relations shown here. So this slide proves that for n is equal to 2, the number of reflexive relation is 4. For this example, we take A is equal to 1, 2, 3, which means the set has 3 elements. So the total number of the ordered pairs in A cross A is 3 square, which is 9. For the relation to be reflexive, every element must be related to itself. So the required pairs are 1, 1, 2, 2, and 3, 3. After removing these three required pairs from the total 9 pairs, we get 6 optional pairs. Each optional pair can either be included or not included. So the total number of reflexive relation is 2 to the power 6, which equals 64. Therefore, for n is equal to 3, there are 64 reflexive relations. This slide shows an example of a reflexive relation when n is equal to 3. Here, the relation R contains the pairs 1 1, 2 2, 3 3, 1 2, and 2 3. A relation is called reflexive when every element is related to itself. So for the set 1 2 3, the pairs 1 1, 2 2, and 3 3 must be present. In this example, all these diagonal pairs are included. So the relation is reflexive. The other pairs like 1 2 and 2 3 are extra pairs that can be added. So this slide helps us see that a reflexive relation must contain all self pairs.
Hello, it's Didar. My previous mate already explained the exemplary part. Now I am describing the remaining part of this project. This slide explains the diagram representation of a reflexive relation. The loops show that each element is related to itself, which makes the relation reflexive. The arrows represent optional relations between different elements. So this diagram helps us understand visually that reflexivity depends on every element having a self loop. This diagram represents a reflexive relation. The loops show that each element is related to itself, which is the key feature of reflexivity. The arrows indicate optional relations between different elements. So overall, the diagram helps us clearly visualize how every element connects back to itself in the relation. This result table shows how the number of reflexive relations increases as the set size n. First, the total number of possible order pairs is given by n squared. Out of this, n pairs are required because every element must be related to itself for the relation to be reflexive. The remaining pairs are free pairs, which may or may not be included. Because of this, the total number of reflexive relations grows very quickly, from 1 when n equals 1 to 4, 64, and then 4096 when n equals 4. This discussion explains why counting reflexive relations becomes simpler once we understand their main rule. In every reflexive relation, each element must be related to itself, so the diagonal elements are always included. These are fixed and cannot be changed. After that, we only need to consider the remaining pairs. Each of these pairs has two choices. It can either be present or absent. That is why the total number of reflexive relations is expressed as a power of 2. As the value of n increases, the number of possible reflexive relations grows very rapidly. In conclusion, the project helped us understand reflexive relations and how to count them. We found the general formula 2n square minus n, which tells us the number of reflexive relations on a set with n elements. We also verified this formula using small examples, which made the concept easier to understand. Through this project, we learned not only about relations and reflexivity, but also about counting methods in mathematics. Overall, the study shows how a simple rule can lead to a clear formula and a deeper understanding of mathematical structures. So it's all about from us for this project. Thank you everyone.